Alfred Wegener Institute, and today I am talking about estimation of spatially and temporally varying parameters in ocean biogeochemical models. I acknowledge my co-authors, Christoph Völker from also Alfred Wegener Institute, Mihalis from University of Bremen, and Lars Nerger also from AVI. So, ocean biogeochemical models are especially integrated model that describe the constitute of biogeochemical or transformation of biogeochemical constitute. The biogeochemical constitute usually include phytoplankton, zooplankton, nutrients, trace gases, and also, of course, the carbon cycle. So here is a model we have at our institute, the regulated ecosystem model version 2, RECOM 2. In RECOM 2, we have two phytoplankton groups. We have nutrients around nitrogen, silicate, and iron. From iron, we take iron from the dust deposition, and also, but the other nutrition we don't consider the deposition in that from the atmosphere. And the matter flow from the inorganic nutrient to phytoplankton. Then phytoplankton takes up energy from sunlight and they grow, and then they are eaten by zooplankton. When those phytoplankton and zooplankton rise, they became nutrients, detritus, and that might sink and remineralize, goes to back to the nutrients. The zooplankton and phytoplankton also excrete, and they also again goes to the nutrients. So we got a cycle buildup, and each of the cycle or each of the arrow in this cycle in the process are represented by the simplified schemes known as parameterization, and they have one or more parameters. That's why in the ocean biogeochemical model we have numerous parameters, and the values of these parameters are not precisely known. And in turns, they translate possibly significant uncertainty in the model outputs. The values of these parameters are actually depends on the biological and physical condition of this of particular area of interest. But in practice, the available reference values come from laboratory experiment or limited field data, and used as a constant parameter value in the model, uh, keeping the values constant in space and doesn't change over the time. So in this study, our objective is to estimate especially and temporally varying parameters in a global ocean model, and to learn from the parameter from the variation of the parameter beyond the parameter values. We coupled RECOM 2 with MIT general circulation model in a lat long cap grid model. It's LLC90 grid model. So in LLC90 we have actually 5 phases. The specialty is the Arctic cap we have here, and these 5 phases divided into 13 tiles is of the tile with 90 times 90 grids, and in the model we have 50 vertical layers. And the over the globe, the model have more than 60,000 white point. That means actually it make the system really high dimensional. So the horizontal resolution of the model Badges especially, we have especially from 22 to 110 kilometers. So we have the finest resolution in the uh, high latitude and the coarse resolution in the mid latitude areas. We drive the model with the atmospheric forcing, internal bearing atmospheric forcing from the ERA 5 dataset. We assimilated 5 days satellite chlorophyll concentration from ESA climate change initiative ocean color dataset, time series dataset. In the right hand side, we can see uh, the climate change initiative ocean color chlorophyll concentration from March 30th March 2018. And this product is actually, so we take the 5 days average values, and this product is composite product of the all available sensor and comes with the uncertainty information. And the uncertainty information we applied in the data simulation. So we used the ensemble data simulation method, and the filter we used is error subspace transform carbon filter that is provided by the parallel data simulation framework PDAP software. So PDAP is an um, free and open source software, and anyone can go to the PDAP website and register and can get code. We use uh, 25 ensemble members, um, to, and we generate the ensemble by perturbing 9 biogeochemical parameters. And the parameters we selected based on a global sensitivity, variance-based global sensitivity analysis. Uh, in the data simulation, we update 8 state variables together with these 9 parameters. And we conducted the data simulation experiment for 1 year from January 2021. We applied the data simulation in log transfer concentration, and the parameter also we transfer log transfer to guarantee that it never goes the negative, or we never get the negative values. So here is the surface monthly mean surface chlorophyll A concentration uh, for April 2021, and this top left figure we can see the free run. Uh, Top right, this plot is for observation, the satellite observation, and the bottom left one is the data simulation analysis. We can see that the free run actually perform very poorly, uh, and but data simulation bring the model reasonable. And the RMSE is calculated against satellite data, and we can see that data simulation reduce the error almost more than 50%. Yet in the bottom left figure, we can see that um, we have a discrepancy of 0.5 milligram per meter cube or more in some regions here, and also here we can see. So as we estimated 9 parameters, here I will show you 3 of them as example and how they behave in this in the system. So this is the phytoplankton parameter, maximum photosynthesis rate of nanoplankton. So the one phytoplankton group. Maximum photosynthesis or the primary production is proportional to the maximum photosynthesis rate. That's why the higher the value of this parameter, the higher the production in the ocean. So we can see that in the equatorial Pacific and also in the North Pacific, we have the continuous upwelling and a strong convective mixing, which fuel the phytoplankton growth, and that is increase the value of this parameter, or that has increase the value of the parameter. And in the oligotrophic region, for example, in the North Atlantic or in the equatorial sub-equatorial Pacific, the low supply of nutrients lead to low production. That's why we get uh, lower value of the parameter, and that's actually makes perfect sense for biogeochemical perspective. But we can see that in the uh, no, further north in the Atlantic and also in the southern ocean, where we have the um, uh, uh, um, overestimation of chlorophyll. There, the data simulation actually result unrealistic parameter values. So, in this region of water deficit, but overall, the values vary within 1 degree of magnitude. That is also from a in situ observation by Mamnun and Holling, they also get similar type of variation over the ocean. And the next parameters I show you is the maximum chlorophyll to nitrogen ratio, also for the nanoplankton. In the RECOM, chlorophyll synthesis is coupled um, to nitrogen uptake, and the uptake of nitrogen by the phytoplankton is then converted to the chlorophyll with this parameter. That's why the higher the value of the parameter, the higher chlorophyll uh, in the mode in the model. So in uh, nitrate depletion region, for example, in the uh, equatorial Pacific or in the Indian Ocean, the model, uh, the data simulation decrease the value of this parameter to compensate the overestimation of the model. And in the Pacific coast of America and South America and in the Southern Ocean, we get though here we have high nutrient, but we have low chlorophyll concentration, and to compensate this low chlorophyll in those regions, data type simulation actually uh, increase the value of this parameter, and that completely makes sense. But in general, we don't have much observation of this parameter, so we can actually cannot verify our parameter with the observation. The last one I want to show you is the maximum grazing rate of zooplankton. So zooplankton eat phytoplankton. So that is the grazing. So the more grazing rate, the less phytoplankton in the ocean. That's how this maximum grazing rate regulates the phytoplankton biomass in the surface ocean. In the subtropical Pacific, here and in the Southern Ocean, the grazing rate of this grazing rate increases by the data simulation. That's why uh, the the grazing rate is low. That's why it increases the phytoplankton biomass. But in the North Atlantic, here, uh, mo- though the phytoplankton is actually, we have low productivity, but most of the phytoplankton is consumed by the zooplankton through grazing. and we get actually really high grazing parameter. Uh, and grazing rate here, and that's also consistent with the observation in the Bermuda station by Nerger and Murali in 1998. And in the Southern Ocean, the reduced grazing rate actually surface phytoplankton biomass, which is also consistent with the recent studies by Caracas et al. In 2022. And in the subtropical North Pacific, uh, here and this region we get also unrealistic parameter value, very high grazing rate because of the model deficits. In summary, uh, we estimated 9 spatially varying biogeochemical parameters, variable parameters below in the model, um, or estimated parameter value in the model point out the essential impact of the data simulation system or of our data simulation state. Estimated parameters point to the variations that is also similar to the in situ measurement. Data simulation leads to somewhat unrealistic parameter where parameter values in the region of model deficit. And finally, we can say that inclusion of the especially varying parameters improve the simulation of especially varying biological uh, productivity in the model. Thank you all.
Thank you, Nabir, for the presentation. Very nicely done. I can see there are already some questions in your part. So I guess I will just read the question to you directly. First one comes from Dan Lee from UK Met Office. The question is, there were some linear structures in chlorophyll field in the control, which looks a bit strange to me. What could be the possible cause of that? And he says he understands a simulation is able to remove these features.
Okay, this actually came from the transition in the from the nitrogen limitation to iron limitation area, and in the model, the grid cell have this transition. Where there we have this type of feature, but we for the pre-run model we don't we cannot resolve those actually. But luckily, data simulation can resolve those those features.
So it's more like a model deficiency.
Yeah.
Thank you. The second question from Moha. The question is, I'm assuming you're doing localization given the small ensemble size. Do you localize the parameters the same way you localize the state variable? Also, do you think the unrealistic updates are due to the log transformation?
Okay, for the past problem, yes, absolutely. I forgot to mention that we localized both state uh, and the uh, and the parameters with the five times five times the grid resolutions. So in the grid, we we localize its 5 times of the resolution, and we localized the same for the state and parameters, but we didn't actually investigate whether it have to make it difference will make any difference. But yeah, we can look at this in the future. And for the log normal transformation, yes, for the chlorophyll, we know that it's this log normally distributed, but uh, for the parameters, we don't know the distribution really. But if we don't use the log normal transformation, we get actually in some grid point, we get negative values for some of the ensemble members. That's why we took the log normal transformation to guarantee that we never get the negative values.
Thank you very much. So I suggest we move on and to the next talk, and for the sake of time. Thank you again, Nabir.